Hello, welcome to the presentation Space Neuron Flight Dynamics Prediction for Virtual Flight Testing. I'm Lilia Jemai, Partnership Advisor at IVADO, and I will be the moderator for this presentation. Quick reminder, 25 minutes, including questions, no audio on participant side. The participants may ask questions to speakers using the question tool, and any time of the presentation, please simply write down questions on swap card and I will transfer them to the speaker. Un petit rappel, les présentations durent 25 minutes, pas d'audio du côté des participants. S'il vous plaît, posez vos questions dans l'onglet questions. La prochaine présentation sera donnée en anglais uniquement, accompagnée de diapos en français. So our next presentation will be given by Ali Elawad. Ali has a bachelor degree in mechanical engineering and he is chief product officer at Dataperformers. Ali worked extensively on designing space systems such as the Cube satellite. He now conducts research nested at the intersection of AI, computer vision, and aerospace. As a CPU, he leads product initiatives pushing the bounding of AI adoption in industrial applications. His background enables him to bridge the gap between computer vision and practical engineering problems. I give you the floor, Ali, to present.
Thank you, Lilia, for the presentation. I would start the presentation with explaining Space Neuron and how it came about, actually. So if you take right now the world of simulation and aircraft certification in general, the first of aircraft models, so those are new aircrafts, most of the testing is done in a physical way. Aircrafts are flown and data is collected, and how this is how actually the aircrafts are being qualified and certified. And the problem with this, it's a very costly and lengthy process. It's also very risky for pilots to fly aircrafts at the early stage of its design and basically fly to see its performance. Also, it's a very costly process. There's a lot of iterations involved, and there's a lot of back and forth between design and those tests. And the last part is looking at the time span it takes for developing a new aircraft. You're looking at 5, 10, 12 years just work involved in this process. And we're here to reduce that and cut the time it basically require to certify an aircraft. Basically, what right now, the state of the art right now of this practice is that simulation is viable, and in a lot of cases you could substitute certain types of required certification. The issue is up till now it requires a huge amount of data that is hard to come by, and also to collect this data in a clean way and to build a model out of it is as lengthy as doing the standard methods of aerodynamic modeling. So what we're bringing here is Space Neuron, and it's an AI-enabled high-fidelity aircraft, basically behavior analysis and also aerodynamic modeling, as well as building some sort of a digital twin of what the aircraft is basically performing or doing at any given time. The way we build this is through the following. We ingest the data from the flight itself. So you're looking at the telemetry of the flight. You're also looking at control data, and then we're ingesting that and trying to build an aerodynamic model of the flight, or a subsystem prediction, the performance of a specific subsystem in the aircraft. This is fed into the AI training, and there's multiple ways we go about this. These models that are designed to be general purpose that would work at, let's say, a specific class of aircrafts, and these models that will work at specific types of aircraft, specific models and some specific classes. Also, what we expect from this is a reasonably performing aerodynamic model that is able to predict the outputs of the system at any given time, given only, for example, inputs, and a feedback loop of the location or the exact position of the aircraft and the exact values of its outputs. You're looking at basically positions and accelerations, and in the controls, you're looking at all the control inputs. Also, this system enables us to build simulators quite fast. What you're looking here is basically building aerodynamic model within a few months, and given that you have the right type of data as an input, and building a simulation model based on that, a high fidelity simulation model. So what is the future of this this technology and this concept? Right now, simulation is basically allowed for certification, but it's really hard for aircraft manufacturers, OEMs, and anybody who is in the business of aircrafts to build a high fidelity model that is purely virtual. And the reason why is because it's really highly dimensional, these models, and they're very hard to articulate, and actually having a model to represent them properly. So part 60 of the FAA certification allows us to do that, but till now nobody really took in the challenge of figuring out this problem. Also, this system could also help in the certification of aircrafts in general, not just aircraft simulators. So it could take some of those maneuvers that are generic or high-risk maneuvers and actually make them virtual tests in the future. So this type of domain still is in infancy, and it needs some sort of early adopters to try it on. And the hope is later down the line, part 23 of the FAA certification, which is basically certifying aircrafts, could be done using at least a couple of those maneuvers could be done using purely simulation data. So what we're really ultimately trying to do is feeding basically our historic data and real-time telemetry data and building a very high fidelity digital twin. That's what's the main aim of Space Neuron. And also that's what we do in general at Dataperformers. We do a lot of digital twin, and that's that explains also some of the intro information about my interest in computer vision, is how do you represent the real world with a virtual parallel that highly represented, and you can use it to build all types of simulation, and in this case, as far as certification down the line. So we're going to dig a bit deeper into the technical overview of the technology. So right now, the simulation and the aerodynamic modeling is mostly done using system identification and some concepts of machine learning. We are here to bring a new way of kind of combining this traditional system identification and machine learning to build pretty, let's say, reliable and robust, useful type of models that could basically build the aerodynamic model for us purely from data and a little bit of system identification, which is understanding the physics of the problem, having it as a pre-step to the AI model building. So let's take a first use case. So we're trying to build the aerodynamic model of the aircraft itself. So we're trying to build a representation of what would be the movement or the maneuver or the state of the aircraft at any given time. So what Space Neuron could allow us to do is build that. Right now we're at the early stage of the results in this exact use case. It's the hardest, but it's kind of like the ultimate goal of this technology. Because you have a lot of parameters in the aircraft, you have a lot of inputs that could influence the output. But at least for standard maneuvers, you know, taking off, landing in normal like air speeds, we can predict with high fidelity what would be the output given the inputs and the previous outputs of the system. The second use case, you're looking at using the engineering parameters that we can get from our design itself. We're looking at the early stage of even the conceptual design of the aircraft and trying to predict the performance given some past data from similar aircrafts. So this particular use case is very useful so that companies could get a head start in building simulators, and they could get a head start also in knowing what it takes to qualify an aircraft, maybe reducing some of the amount of physical flights they would have to fly. And the third application is prediction of part failure. So as a byproduct of building a digital twin of high fidelity is part failure could be predicted much more easily. And using this system, one of our short-term goals is to work towards the parts prediction, parts failure prediction, because it's less complicated than the full aerodynamic model. It also is isolated case. Most of the time you're interested in the failure of a specific component, so we can hone in and basically build a more robust model for that. The fourth case is, improving the efficiency of the flights. Knowing how this flight has been flown and the previous flights, we can also predict if the fuel efficiency is, what is the recommended, usage of the fuel, and knowing that if the aircraft is actually using more fuel than the flight requires. This takes into consideration, of course, the maneuver itself of the aircraft during its flight, and trying to learn some sort of a reference of what would be a fuel-efficient flight. And this, of course, has its benefit into reducing the overall costs for operators. Some of our early results of this system is very promising. For standard maneuvers, the system was able to predict the aerodynamic model quite well. And we're talking about a helicopter here. This is not for fixed wings, which we expect them to be much easier. So some of these results are basically a combination of some are purely using WaveNet, and some are using fully connected layers. Basically, what we aim to do is finding the right balance between the approach of system identification and machine learning to come up with the most high fidelity, basically models that run in real time in a very efficient way and a very responsive way, because we're hoping to have this mounted on the aircrafts and being used in real time. Looking at our roadmap right now, we're looking at, we've completed the proof of concept of the first stage, which is some of the maneuvers in part 60 of the FAA, which is the required certification for simulators. The second phase is phase 2, which trying to move into some of the predictive maintenance applications and the fuel consumption reduction. And then later we want to basically build the right knowledge and the right understanding of the aerodynamic models to move towards tackling the FAA Part 60 certification and try to pass that for the simulators, and moving on slowly towards certifying the aircraft, some of the maneuvers of the aircraft itself. Of course, this timeline is really depends a lot of the industry standard itself. I mean, some are accepting to this type of new applications, some are not, but we are here. We worked on this project with the National Research Center. It's actually one of their interests to develop this type of technologies and push it further, because it has big implications for the local market, for the design of aircraft manufacturers. It speeds up the time to go to market and just increase the competitiveness of the Canadian market. Thank you very much.
Thank you so much, Ali, for this very interesting presentation and for these use cases. We have some questions. The first one, the scope of Space Neuron is for stability and control SNC certification testing. Could it be used for subsystem certification, example, hydraulics, fuel, avionics, etc.?
Absolutely. I think that's actually one of the applications that are, I would say, lower hanging fruit than the full system, because you're looking at a specific set of parameters and you could predict with high fidelity those subsystems. We are looking for basically adopters in that arena, and yeah, please contact me.
Perfect. Please, for all participants, you can ask your question under questions box of Swapcard. So the next questions, during the aircraft development, the aerodynamics change between the earlier and later control laws. Can Space Neuron update its model when the control laws are more mature?
Yes, that's the benefit of this actually approach, is long as we're feeding new type of data to the model. So you can think of it, in the beginning, you're learning like a rudimentary representation of your aircraft. So it's less tuned. As you feed more data, it's learning the new concept of what the aircraft is, and you can continuously add this data and improve the model as you go along in your development cycle.
Thank you. So did you have issues in collecting data to be able to do prediction? So are you using real data or simulated data?
Good point. We started with data and actual helicopter data, and we found also simulated data is very interesting. So the flight simulators that are available right now in the market, they help quite a lot. So we had one of our team members fly an aircraft to enhance the data that we have, but we found it sufficient enough. I would say the most critical point is explainability of this type of data. So if you know exactly how this data came about, how the flight was, then it's easier to build a model from it. If the data was run for, let's say, a whole flight without understanding which maneuver is which, this could get a bit tricky because it needs some sort of, like, let's say, annotation and splitting of the data to represent different maneuvers. As we move towards maybe learning the full flight as one shot, that definitely somewhere down the line in the future, as we learn more and more about the overall behavior of, let's say, fixed wings or helicopters.
Thank you so much. Maybe a most general question. What was the biggest challenge of in this kind of project?
I would say in this exact project, the main challenge was understanding the physical system. Coming from, if you're looking at it from a machine learning point of view, the data was not performing at all because we did not take into account the physical system. For example, the controls of a helicopter really represent a very, very specific set of inputs that to correlate it to the output, you would need to develop some sort of a lot of pre-processing to ingest that. And I think that was the main challenge. Two, there's a concept called to trim the aircraft, which is like the initial point that you start your prediction from. That's hard because to trim the aircraft is to actually have fixed value, to know specific values for all the parameters. And that's one of the very hard concepts related to aerodynamics in general and simulation. So that was always hard to get it right because, you know, it's a 6 degrees system and it just changed.
That's perfect. I think we are at time. Thank you so much, Ali, and nice to discuss with you today. Hope to see you soon. Thank you so much.
Thank you.